Hello everyone, welcome to lecture 44 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on metamaterials based nanoscale optical cavities, and we will also discuss some active hyperbolic metamaterials. So here is the lecture outline. We will continue our discussion of how metamaterials can be used for optical cavities that can be scaled down to nanoscale. We will discuss the design of metamaterials based nanoscale optical cavities. Okay. We will cover hyperbolic metamaterials for optical cavities, discuss their permittivity and dispersion relation, and also the mechanism for total internal refraction that allows it to work as a cavity. After that, we will discuss active hyperbolic metamaterials and what are the applications of active hyperbolic metamaterials. Now, we have seen that hyperbolic metamaterials enables interesting applications due to their hyperbolic dispersion, right? And one of those could be towards miniaturizing the optical cavities that will increase the photonic density of states, which in turn will increase the light matter interactions, very useful for optoelectronic applications. However, in conventional cavities, the scaling is typically limited by the diffraction limit of light, and it reduces the quality factor. So, you can think of optical cavities made of indefinite or hyperbolic metamaterials that can confine electromagnetic field in extremely small space, okay, by overcoming the diffraction limit barrier. So, it also shows some anomalous scaling laws, something like the cavities of different sizes can be made to resonate at different frequencies, and also the higher order mode will be seen to resonate at lower frequencies. This is something completely opposite that happens with conventional cavities. Okay. You will also see that you can make cavities with sizes down to lambda by 12. So, that means you are basically going to achieve ultra high optical indices. Okay. So, in the conventional cavities such as microspheres, microtoroids and photonic crystal cavities, the index is basically limited by the natural material, and that also defines the physical size of the cavity, which remain typically in the wavelength scale. But because with metamaterials you can achieve very extraordinary indices, optical indices, that is how you can also change the overall physical size of the cavity. So, here the metamaterial structure basically consists of alternating layers of thin silver and germanium. Okay. So, as you can see here, this is the direction of K light propagation, this is the electric field direction, and this is the magnetic field direction, right. The electric field is basically considered parallel to the interface between the metal and the dielectric layers. Now, we have to consider the period of this multi-layer, okay, much smaller than the wavelength. The period is nothing but the thickness of the germanium plus the thickness of the silver layer, because that is the unit cell that is being repeated periodically in one direction, right. So, when the multi-layer period is sub-wavelength or much smaller than the wavelength of the light it is interacting with, the structure basically behaves as an effective medium, and it will be safe to use the Maxwell-Garnet theory for estimating the effective permittivity along the parallel and the perpendicular direction, which we have seen couple of times by now. So, this metamaterials permittivity tensor will be uniaxial, because along the two parallel direction they will have same. So, x and y will experience the same kind of permittivity. So, it will be epsilon parallel, and along the z direction you will have different permittivity, which is epsilon perpendicular. Now, because it is a metal dielectric kind of interface, okay, you will see that one will be positive, the other one will be negative, okay, and that is when this the principal components have different signs, you get hyperbolic dispersion curves, right. So, this basically creates this kind of type 2 hyperboloid isofrequency contour, right. And for comparison, you can also see there is a small spherical isofrequency contour shown here for air, where the radius is in the K space, the radius is k naught, that is 2 pi by lambda. Okay. So, you can see this isofrequency contour of this multilayer metamaterial, which is basically taken from this dispersion relation shown as this blue surface, right. And the yellow dot here is located on this hyperboloid that shows the resonating wavelength k that is inside the cavity. Okay. So, you can see that this is much larger than the k naught, indicating that in this kind of material you can have ultra high effective refractive index, which will be given by n effective as k by k naught. Okay. So, the open curved hyperboloid dispersion also allows waves with extremely large wave vector to propagate, okay, which means a large momentum mismatch at the metamaterial air interface will be there, and that will lead to total internal reflection, right. So, by cutting the metamaterial into sub-wavelength size cubes, okay, what you can make a 3-dimensional fabric barrow cavity kind of structure, where the effective refractive index can be given as k by k naught, as we have seen. Okay. So, because of this extremely large wave vector k, okay, that is coming from this unbounded isofrequency contour hyperboloid. So, the cavity size this will be very high, and that will make sure that the cavity can be squeezed to very small size or nanometer scale, right. So, now let us look into the permittivity and dispersion relation for hyperbolic metamaterial with this particular example, where silver and germanium layers are basically alternating. So, we have learned that you can model this using Maxwell-Coordinate equation. Okay. So, you can use this particular equation, epsilon parallel, that will be along x and y axis. So, you can also write them as epsilon x equal to epsilon y, that will be equal to p epsilon m plus 1 minus p epsilon d. Okay. What will be p? P is basically the filling fraction of metal, right. So, 1 minus p will be the filling fraction of the dielectrics. Okay. So, epsilon perpendicular can be written as also epsilon z, because that is along the z direction, that is epsilon m epsilon d divided by p epsilon d plus 1 minus p epsilon m. Now, if you take p equals half, that is when the two layer thicknesses are of the same size or the same thicknesses, then you can have a simplified version of this equation, right. So, this is a generic form, and why it is important? Because you will see that in this particular equation you are also using a metallic permittivity epsilon m. So, because you are using silver, you can use Drude model for describing the optical properties of silver. So, you can use this formula epsilon ag, that is your epsilon m here, that can be written as epsilon infinity minus omega p square divided by omega square plus I omega gamma. So, epsilon infinity is the background permittivity, okay, which is 5 for silver. The plasma frequency is 1.38 into 10 to the power 16 radian per second, and the collision frequency gamma, that is given as 5.07 into 10 to the power 13 radian per second. So, with this you can put it here and you can calculate the values. Okay. So, for that you also need to know what is the permittivity of germanium, that is your dielectric permittivity, taken as 16. So, let us take an example where the filling fraction is 0.4. Okay, that is the metal filling fraction is 0.4. So, if you calculate the permittivity components at a given frequency, say 191 terahertz, which corresponds to 1.5 micrometer vacuum wavelength, you will see that epsilon parallel, which is epsilon x or epsilon y, that comes out to be minus 41 plus 2.2 I. So, that is basically the permittivity along the layers, and that is coming out to be negative, and the perpendicular one is coming out to be 29.1 plus 0.1 I. So, the I is missing. Okay. So, that is basically positive permittivity, right. So, this ensures that, so this is the plot that shows you the variation. Okay. So, we are considering at 191 only. So, that is somewhere here. Okay. That value is shown here. Okay. So, this particular dispersion relation, which is plotted in x z plane can be written as kx square by omega z, kx square by epsilon z plus kz square by epsilon x or epsilon y, because they are same, will be equal to omega square by c square. Now, for the 3-dimensional Fabry-Perot type metamaterial cavity, the resonant condition is that the round trip phase, which is 2 ki li, should be equal to integral multiple of 2 pi, that is you can write as 2 mi pi, and that should happen in all the 3 directions. So, here I will be x, y and z. So, li is basically the cavity size, okay, and mi is representing the mode order. Now, the resonant wave vector for the cavity mode can be written as ki by k naught, which is approximately mi lambda naught divided by 2 li, right. So, here k naught is nothing but 2 pi by lambda naught. So, you can actually use this and understand the resonant wave vector for the cavity mode. In this particular figure, it basically shows you the dispersion relation in the k space for the hyperboloid or hyperbolic metamaterials that is shown here, right, which has got this kind of effective permittivities. Okay. So, what is noticeable here is that the hyperbolic isofrequency contour is basically rotated by 90 degree with respect to those we have seen for the hyperlengths, right. So, as a result, you can see that this is in kx and this is kz. So, this is basically in the xz plane. Okay. So, you can understand that this particular hyperbolic metamaterial can confine light in the xy direction instead of propagating along the z direction. Okay. So, the figure A, this one shows you the 3D hyperboloid isofrequency contour for this kind of hyperbolic metamaterial. So, this also tells you about the large wave vectors that are being supported in all 3 directions, and you can see that the kz can be comparable to kx and ky, right. So, what is important here? Then you can basically cut the infinite medium into small cubes, and that will form 3D Fabry-Perot cavities, right. So, how it works? They works on the basis of total internal reflection that will occur at the air metamaterial interface, okay. And you will see that the hyperbolic isofrequency contours here are the open ones, so they are not closed, okay. That means the propagation is forbidden in some direction, okay. So, that also results in varying the total internal reflection condition based on the direction of the propagation. Basically tells you about the schematic of the TIR mechanism, okay, that is useful for constructing the cavity. So, this is what is happening at the different corners. So, this metamaterial and the air interface will support total internal reflection, mainly based on the huge difference between the supported wave vectors. So, this also results in direction dependent total internal reflection conditions. So, we will establish that dependency here. For the top and the bottom facets, which are basically parallel to the multilayer, you will see that no mode in air matches the parallel momentum, okay, in this indefinite medium, okay. So, these facets will basically reflect light from all allowed incident angles. So, there is no issue with the top and the bottom one, right. Now, for the side walls, the total internal reflection, that there is a critical angle involved, that is theta c. You can calculate this as tan inverse square root of epsilon p divided by epsilon v times epsilon p minus 1. So, here it gives you this is coming from the condition that your kV is greater than k naught. So, what is kV? That is basically the vertical wave vector, you can also call it as kz, okay. But here we are just telling you about Kv, V stands for vertical in this case. Okay. So, in this equation what you see epsilon P is basically the effective permittivity that is parallel to the multilayer. So, it is epsilon x or epsilon y. Epsilon V is basically the vertical permittivity, or you can say the effective permittivity that is perpendicular or vertical to the multilayer. So, these values can be estimated using effective medium approximation, and after that you can calculate what is the total internal reflections critical angle. So, any angle that is above the critical angle will get total internal reflection, and that is applicable for the side walls of the cavities. So, with that we understood the mechanism behind the hyperbolic metamaterials that can be used for making sub deep wavelength nanoscale cavities. Now, we will move on to discussing active hyperbolic metamaterials. Now, till now we have seen conventional hyperbolic metamaterials which are made of alternating metal dielectric multilayers. We have seen they could provide fixed hyperbolic dispersion over broad spectral range, typically from UV to infrared, and this dispersion properties are predetermined during the fabrication by the choice of the material and also the choice of the thickness, that is the filling fraction. So, what are the limitations? So, this hyperbolic dispersion remains fixed and you cannot alter it after the fabrication is complete. So, normally in any kind of dynamic application there is need of tunability, right. So, if you think of future reconfigurable photonic devices that will require tunable hyperbolic dispersion which can be actively tuned across wide spectral range. So, you can think more on top of conventional hyperbolic metamaterials where you can incorporate some functional materials into those hyperbolic metamaterials which will enable you to tune hyperbolic dispersion without altering the composition or the physical structure. Okay. Tunable optical properties of hyperbolic metamaterials enable a range of potential applications which we will briefly see in this lecture. So, active hyperbolic metamaterials can be used in different spectral bands. They can be used for reconfigurable sensing, they can be used for supercollimation of terahertz light, useful for modulators, terahertz modulators. So, we will take up some of these examples. The first one is reconfigurable sensing. So, reconfigurable sensing is demonstrated using an active hyperbolic metamaterial for highly sensitive biosensing of small molecules via Gush-Hansen shift. Okay. That is basically using active, this is called antimony trisulfide hyperbolic metamaterial. So, the technique here uses Gush-Hansen shift, in short you can call it GH shift, that basically measures the lateral displacement of the reflected beam near the coupling angle at the interface of two media, right. We will show you an example in the subsequent slides. So, there the bulk plasmon polariton which is called BPP mode in the hyperbolic metamaterial gets excited using the prism coupling mechanism, right. So, we will discuss about how the experimental setup looks like. So, you can use P polarized, there is a TM polarized wavelength light, the typical wavelength of say 632.8 nanometer, this is the red wavelength, okay, red wavelength, and you can use it in the hyperbolic region of the hyperbolic metamaterial. And then you use prism coupling that can excite the bulk plasmon polariton mode within this hyperbolic metamaterial. So, this bulk plasmon polariton basically refers to a type of metamaterial structure, this kind of BPP HMM basically tells you about a type of metamaterial structure that can exhibit both hyperbolic dispersion and also support propagation of this bulk plasmon polariton modes. So, the prism that you are using for coupling that can be made of BK7 glass, okay, which has got a refractive index of 1.5. That is used to ensure momentum matching, because your HMM has a lower refractive index, as you can see here. So, this particular plot shows you the real part of the uniaxial permittivity of the different components that is used in this metamaterial, which is made of antimony trisulfide and titanium nitride. Okay. So, the different colors basically show you that the red ones basically tell you about the antimony trisulfide in amorphous, and the other one shows when they are in the crystalline phase. Yeah. So, this is basically epsilon z, the vertical permittivity, and this shows you the epsilon x or y, that is basically the parallel permittivity. Now, what you see here, this is the wavelength range, and beyond this particular wavelength, this is becoming negative. That means you can consider this region as your hyperbolic region, where one kind of permittivity constant is one permittivity is negative, the other permittivity is positive. So, this is the typical hyperbolic region which you will be interested in, right. Now, if you use this, and this particular setup shows you the experimental setup that has got this prism which is made of BK7 glass. So, once you do that, okay, so it tells you that you keep on varying the incident angle, and you keep on measuring the reflectance angle or reflectance from this side. Only at this particular angle you will see that the reflection dips, okay. And what are these two graphs? These are again the antimony trisulfide is considered to be in either amorphous phase or crystalline phase. They more or less very closely give you the similar kind of dip. So, that dip actually indicates excitation of the BPP mode, okay. So, that energy is basically coupled to the +1 polaritons, okay. So, this minimum reflected intensity, okay, decreases at the resonance angle, which you can also see from here, okay. So, here you can actually see that the GH shift, okay, also happens maximum at this particular angle, okay, around 41 or 42 degrees, okay. So, it also results in a narrower reflection spectrum line width. So, the excited mode is confined to the fundamental BPP mode, which is a low K mode of this antimony trisulfide and titanium nitride hyperbolic metamaterial, okay. The phase singularity at the coupling angle, which you can see here, okay, can be actively tunable by non-volatile phase change of this antimony trisulfide. That means, when the antimony trisulfide can change between amorphous and crystalline phase, that is when you can change this wavelength, and that will actually give you the shift in the properties, right. So, the phase singularity at the coupling angle can be actively tuned, okay, by this antimony trisulfide, as the T and Tm polarized light phase difference shows a sharp singularity at this particular angle, okay. So, this is how you are seeing this tunable Gauss-Hansen shift in this kind of metamaterial, right. So, here again the two graphs tell you about the shift in this wavelength because of the change in the phase of antimony trisulfide. So, the red one is the crystalline phase, the other one is the amorphous phase, right. So, we can observe that this enhanced shift, GH shift or Gauss-Hansen shift, occurs at the BPP mode excitation angle determined by the phase derivative at the coupling angle, right. So, this figure shows you the maximum shift happens when the phase changes sharply, isn't it. So, the tunability of this GH phase is enabled by switching of this antimony trisulfide between the anamorphous and the crystalline phase. So, this is how you can do active tuning. Okay. So, this GH shift scheme also enables high refractive index sensitivity, and it can detect small biomolecules at extremely low concentration. Okay. So, what are the improvement potential? You can think of using longer wavelengths and higher index prism, okay, here to enable tunable range of the shift. So, you can also think of hyperbolic metamaterial based plasmonic platform that can be used for detection of small molecules like exosomes, okay, from bodily fluid using this kind of mechanism. So, this tells you that you can also use active hyperbolic metamaterials for dynamically tunable systems. So, with that we conclude this lecture. So, if you have got any query regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.